Okay, so in this lecture we're going to talk about thermal transduction. Admittedly this is going to be a very quick overview of what happens, especially at microscales regarding thermal transduction. And you guys and gals have taken courses on the topic, right? So it's full course on thermodynamics and issues like that. Over here, we're just going to have an overview of the whole thermal transduction and especially electrothermal transduction, and focus on the applications at microscales. So first issue is heat transfer, right? So when you talk about thermal transduction, you have to talk about heat, where it comes from, and then how it propagates or distributes across the system. When we talk about heat energy, it can go from one place to another through different mechanisms, 3 different mechanisms. The first one is conduction. So basically you pass the heat energy from this segment of the material to the next segment next to it, and the segment next to it, and the segment next to it. So as the cartoon here shows, it's like, people that are standing next to each other, and then they're carrying a bucket of water, or passing along a bucket of water, moving heat energy, in this cartoon the water, from one side to the other side without the particles themselves moving, right? So that's conduction. You pass the energy without the particles themselves moving. This is called thermal conduction. Convection is where the material is heated up and the material itself moves and takes the heat energy with itself. So this is a situation where, for example, you use a fan to blow the air over a, let's say, hot CPU. You remove the heat around that CPU by heating up the air and then moving the air away by fan. And again, the cartoon shows the same thing, that you go and tap into this heat, and then physically the material moves the heat with itself. And then finally you have radiation, where you actually may not have a matter between the source of the heat and then where it ends up. Heat is transferred through radiation from one source to another. So again, in the cartoon, it's basically shooting water to the destination. We talk about all these 3 of the situations, these 3 heat transfer mechanisms at MEM scales. In terms of applications, well, you have thermal sensors that you use in all sorts of applications, and we have thermal actuators. We'll talk about both, but here, to just get started, you can see a IR image sensor, where each pixel in this image sensor is a temperature sensor, a heat sensor, right? And what happens is that when you have an IR source in front of this image sensor, the areas that are hotter on that image, on that subject, or some sections of these sensors, they will receive more heat, the temperature rises a bit more, and then you can create an image out of that heat distribution in front of you. You see that the sensor itself is hanging in a small cavity that we produced here through, guess what? An isotropic etching of the substrate. And that's one part, that it is hanging in a cavity, it's not touching the substrate. And the second part is that, I could have directly connected it to the substrate with 2 short arms here, but I'm not doing that. It's going through a long arm attached to this end and another long arm attached to this end. So that's one design feature you can notice here immediately. For these folks here, for this other sensor here, you notice that the sensor is on an elevated plate. The plate is not touching on the substrate, it's actually elevated from the substrate. And think about why these are like that. Why didn't we make them the easy way, directly on the substrate? We are elevating them or removing the substrate around them to make these sensors. We'll talk about it during the live sessions if you would like to check your answer with me. Now, in terms of heat energy, you can say that the heat energy is always proportional to, or changes in heat energy are proportional to the changes in temperature. So if you have some delta T on some material, the heat energy in that material changes. It is proportional to how much your temperature changed, It is proportional to how much matter you have. So if you raise the temperature of 1 kilogram of water by 1 degree versus 100 kilogram of water by 1 degree, obviously, there is a proportionality to mass. And C is the specific heat capacity of the material, where it is a property of the material, right? It's easier to heat up, let's say, air than it is to heat up water, and then so on and so forth. So it's a property of the material. So it is about how much material you have, what is the material, and how much is the change in temperature. So 3 components. Now, the continuity equation, on the other hand, says that the amount of variations in heat energy somewhere in a material over time depend on 2 parameters. Qgen on the right side, which is how much energy is produced here, right? And this accounts for all sorts of mechanisms to produce energy, right? So you heat. For example, you can have illumination by a high energy laser beam. You can have Joule heating in electrical domain. Any sort of heat generating mechanism goes in Qgen. That basically is your coupling mechanism to other energy domains. And then you have the JQ. JQ is the flux of heat that you're losing from this environment. How the heat that you produce here, how much of it is kept and how much of it is lost is going to determine dQ over dt. If you lose more than you generate, obviously you cool down the system or the particle or the matter. If you generate more than the loss, you heat it up. Usually there's a steady state after a while if things don't change. So you generate some heat, and then you lose some, and then things go and you get some stable condition. Heat flow is irreversible. It's always from the location with a higher temperature to a location with a lower temperature. And is often an indicative of loss in most systems, right? So the energy that is converted to heat, in many cases, especially at microscales, is lost. You cannot recover that energy in most situations. So we really don't like to heat up, unwanted heat up of structures and devices. So let's talk about conduction and convection. What we can have is that the heat equation gives us how the temperature is distributed in an environment, in a structure, right? Is proportional to the changes. So this is basically your MC delta T, the material density, the specific heat. This is normalized by volume, of course, and the changes in T versus time, and the amount of energy, the amount of heat that you produce in that volume, okay? So and kappa here on the left side is thermal conductivity. How fast are you losing this heat to the environment? Or how easily, not how fast, but how easy it is to remove heat from this location to other locations. So the larger kappa, the larger thermal conductivity means that, the material, it's easier for heat to conduct through the material. A small kappa for thermal insulators means that the heat has a difficult time moving. We can solve this equation with different boundary conditions. A couple of common ones are Dirichlet boundary conditions, where, for example, you have a heat sink or a heat source, and the temperature at the boundary is specified, right? So you basically have made this heat sink, you run it, and you figure out, this is the temperature at the boundary. Or you have, let's say, a Peltier element, and you can figure out what the temperature at the interface is. And with that boundary condition, you can go and solve this heat equation, steady state or transient. Newman boundary conditions happen when you have some sort of a thermal isolation around your device. And in this case, well, you do not know the temperature, but you know how much heat is lost at that boundary, right? So dt over that direction is known. So if you have an insulator, you can say that the rate of change in temperature at that insulating boundary is going to be this much, and then you go and solve the differential equation using that. And then you can have convection boundary conditions. These are usually forced, but it could also be free. Free meaning that you heat up the air, it becomes lighter, it moves away, and then you can have convection through that mechanism. Or you can have a fan and just blow air, or water, any liquid would do. So in that case, you have some constant that determines, the efficiency of your convection mechanism. The T at infinity, you're removing heat from here, moving it to somewhere far, hopefully. So what is that far location temperature, and then what is the location at this point? So those are the three typical boundary conditions that you have to solve the heat equation with. And I've put a reference to an online book on heat transfer, which is a really good book, and it is freely available. The 4th edition was available when I prepared these slides. It could be there could be a newer edition to that book at this time as well. So let's just see how this applies to MEMS, right? So this heat discussion or thermal conduction and conduction applies to MEMS. So let's assume that over here I have a beam whose both ends are fixed, and it's made of some conductive material, electrically conductive material. It has some thermal conductivity as well. And I pass a current through this beam. If I pass a current through the beam, because it has some resistance, we know it's going to heat up. And the question here is that what is the temperature distribution on this beam in this simple problem? So this is the problem I need to solve, right? The heat equation. I'm talking about a steady state, so the changes in T temperature over time are 0. So the first term goes away, it makes my life a bit easier. And it's a one-dimensional problem. It's just, the distribution of temperature along the length of that beam. So from that heat equation that looks a bit, intimidating, I come up with this equation here. So the second derivative of T with respect to X, that's the left side of the equation times kappa, bring it to the right side. I have the second derivative of T with respect to X is 1 over kappa times Q gen with a negative sign. Q gen is the amount of heat I produce here. So in this case, what I can do is I have the solution, and you have it on your slide. I just want to quickly show how we can solve this equation. So the second derivative of T with respect to X squared is minus Q gen over kappa. All right, so what is Q gen? Well, Q gen in this case, it's a resistor. It's I squared R. I know that's the amount of power I dissipate on a resistor. But Q gen is normalized to volume. So I divide it by the volume of the beam. And if it is of length L and cross-section A, that's the volume of the beam, LA, right? So that's Q gen. And I squared R is the power that I dissipate on this resistor, electrical resistor. Now I can solve this equation. So let's solve the equation on the left side. What I can do is that, I can see that the left side of the equation is a function of X. The right side is just a constant. So easy solution is to take the integral of both sides, or to integrate both sides. Some constant C1, integrate again, so T as a function of X, you can write to just be explicit if you want. It's going to be minus Q gen over 2 kappa X squared plus C1X plus C2. And that's the solution to the differential equation. Boundary conditions, the assumption here is that the two ends of the beam are constant, are held at constant temperature. Basically, the substrate is so large, such that its temperature does not change with heating up of this beam. The substrate temperature stays the same. So boundary conditions that I have is that T at X equals 0 is, let's just say, T naught, and T at X equal L, the end of the beam, is also T naught, right? So the only changes are along the length of that beam. So if you go and plug in those values into the equation that I have here and use this expression here for Q gen. I'm going to switch back to the slides. You get that solution, right? So you have a temperature that is a function of X, and then if you look at this expression, you can actually go and show that the maximum temperature happens at the middle of the beam, as you might expect here, the farthest from the two anchors at the two ends. And that is it. Basically, that's how temperature varies with X going from one end of the beam to the other end. If you want, you can go and say R is the electrical resistivity, rho E times L over A, and write everything in terms of material properties, rho E and kappa here, and beam dimensions, A squared and L, as shown here. Okay, so just a note here, convection is usually not a concern at microscales. The reason for that is, in most situations, your device is made of silicon and it is sitting on a silicon substrate. And for silicon, the thermal conductivity is quite high. It's actually larger than some of the metals. So you are sitting, or the device is sitting on essentially a heatsink. The rest of your chip and the package and everything else behave as a heatsink. So in most situations, you lose the energy very quickly to this heatsink through conduction. Convection is, well, there is convection, of course, but it will be much, much, much smaller than the amount of heat transferred through conduction. For most situations, we do not really take convection into account. There are actually devices out there that are working based on convection, thermal convection, but for vast majority of the devices, thermal conduction is the one that you need to worry about or to take into account. We also talked about radiation. We also said radiation is another form of energy transfer. The way it works here is that, as you raise the temperature of a device, it starts to radiate some of that energy away in form of a photon. And you can see that, the typical dependency is to the T to the 4. It depends on the surface of the material, the emissivity of the material. And what happens is that, it's basically proportional to T in kelvins to the power of 4. And at low temperatures, anything, less than a few hundred degrees Celsius, this is negligible. In most situations, radiation doesn't come into play for typical MEMS device operation. Okay, there are, again, it has to be said, there are devices that rely on radiation for their performance. The bolometer that I showed at the beginning, it is absorbing heat, right? So it's basically the opposite of this, but it is a radiation heat transfer that you have to take into account. But going back to that same device, once the heat is on the bolometer, once you absorb that heat, it's going to be lost through conduction. And now that should give you an idea why we put it in a cavity or we raise the sensor above the substrate. So we talk about sensing in a second, but thermal actuation is a convenient and simple form of actuation at microscales. What we do is that we heat up a piece of material, a piece of metal or silicon, you get thermal expansion, right? So for most materials, once you heat them up, their dimensions change, usually increase, right? And if you think about the linear situation, you get some thermal expansion coefficient, alpha T, and the change in the length of the material is proportional to that alpha T times the change in temperature. Now, you can take advantage of this to actuate. You can take advantage of this to move stuff in a simple bimorph relay in the old heating element or heating controllers. What you had is two materials with different thermal expansion coefficients sitting in an environment. Once the temperature changed, well, they both wanted to expand, but one expanded more than the other. And then therefore that would just curve up the tip of that beam that if they were glued together properly or fixed to each other properly. And that would be your control mechanism. You know, if the temperature raised above a certain limit, it would just disconnect the circuit so that the temperature would go down again, and this was your control mechanism. You can do the same thing at micro scales. The issue is that the conductors that we have at these levels, the typical devices that we have for micro machine device systems, have thermal expansion coefficients that are fairly close to each other. Right? So you have silicon and some metals and polysilicon. They have more or less similar thermal expansion coefficients, so this is not going to be very effective. An alternative structure is this, where you have a chevron structure. This is called the chevron structure. You pass a current from one end of this to another. Each one of these beams expands a little bit, but if you choose the dimensions and the angles here correctly, you can get a significant amplification of that displacement in this direction. So let's say you can have an amplification factor of 50, so that if this beam, due to the expansion, wants to become longer by, let's say, half a micron, with an amplification factor of 20, you can actually get 10 microns of displacement here. You will have an assignment on this, so I will leave the discussions to a later date where you have looked at that problem, but that's the working principle. This is another approach. You can have two beams of the same material, but one shorter than the other. And then if you pass a current through these two beams and you heat them up, the longer beam will become longer, more than, or delta L over L will be the same, but delta L for this longer beam will be more than this, and therefore the tip of this structure will move to the left. It's a bit inconvenient because the two pads are not the same, let's say, Y in this situation, in this direction, and this is an alternative formulation, right, where you can actually go and make a piece of this structure wider, and therefore the resistance will be lower, and therefore the heat produced over there will be less. Pass a current through this beam. This beam is long and narrow. It will heat up. This part is wide and long. It will not heat up as much, but this little piece here will also heat up. But the net effect of this change in geometry is that this part will heat up much more than this part, and therefore again you will have a movement to the left. Typical heating mechanisms for these kinds of structures is Joule heating. It's the easiest thing for us, pass a current and then produce some heat and hopefully get the actuation that you need. You can also use the dielectric losses. This is the same mechanism that your microwave oven uses to heat up, let's say, water or food. You basically excite the atoms inside the structure at the right frequency so that they start vibrating with the external electromagnetic signal, and in that process they dissipate some of that energy in form of heat. So here's an example for a device that is used as a thermal actuator. Now I like this because not only it shows you the thermal actuation and how this device moves up and down, but it also shows you the dynamics. So let me see if I can play this. Okay, so now I'm passing a relatively slow current, small frequency through this. The tip of the beam starts to vibrate as I increase the frequency. At some point, two things happen. First of all, the vibrations become so fast that the camera cannot capture them, but also the air damping will reduce the signal amplitude. And then at resonance, I will have that larger movement as I expect in the frequency response of the device. Here is another example. This is a device that we made as to measure electric field. For that, we needed to move the center part quite a bit. We needed to move it about 10 microns with the smallest possible drive voltage. And what we did is that we used thermal actuators in this case. It's going to zoom in, and you'll see that that chevron actuator on top, middle top, is the part that is producing the displacement, but the displacements are small. So what we did is that we used the mechanical amplifier there to increase the few let's say microns of displacement that we could get, or less than a few microns of displacement that we were getting from the chevron actuator into a noticeable displacement of the shutter that was shown in the beginning of this video. Okay, so now when we talked about transduction and energy transfer between different domains, we have a strong coupling between the thermal domain and electrical domain. So if you go back and look at your basic equations for voltage across a resistor, in electrical circuits, you saw that, the voltage across a resistor is proportional to the resistivity of that material and the current. Sorry, voltage across a resistor is Ri, resistance times current. If you want to go into a material and normalize everything, the localized changes in voltage or field are proportional to the resistivity of the material times the current flux, right? So this is Ohm's law. And then on the thermal side, we saw that if you do not have a generator, the change in heat, the change in temperature is proportional to the flux of heat away from your that portion of the material, right? We are looking at the segment of this material. So JQ is the heat that you're losing, and therefore your temperature variation will depend on that. Now, these were the two independent equations, one in electrical domain, one in thermal domain. But we know that, okay, so if you have a resistor here and you have a temperature distribution along the length of this resistor, you actually will produce a field, even if there is no current, right? So there is a dependence. And why is that happening? Well, think about electrons. Let's say you have a heated end and a cold end for this resistor. The heated end will have higher energy electrons. They move farther, they move more. So you expect some of them to move away from that heated end towards the cold end. And because your electron distribution is not uniform anymore, it's not the same all across this piece of material, you will get an electric field. So the voltage that you measure across this piece of material is now a function of the temperature difference between the two ends as well as the current that goes through it, right? On the thermal side, well, we saw that, if you have a generator, Qgen, the heat flux or the temperature distribution depends on how much heat you produce and how much heat you lose. JQ is the heat you lose. If you have a current going to a resistor, you produce heat. And then we actually solved the problem based on that just minutes ago. So in that case, again, the electrical domain is coupled to the thermal domain. So these two equations show you how these two domains are coupled. We use the top one for sensing and the bottom one for actuation. What does thermal actuation mean? It means that I can actually control the heat flow using a current. And you use that in Peltier element. I'm not going to get into that discussion anymore, but with the Peltier element, you can actually heat up a place or cool it down, right? By just passing the current in the right direction. And that is the coupling that you see there. The top one is the top equation is the one that I'm going to focus on, where you have a voltage proportional to the temperature difference across the material. Alpha S in this case is called the Seebeck coefficient. It's a property of the material, and we obviously, if you want to make a sensor, we would like to have a device where you have a large alpha S. So for a given delta T, you get a larger voltage. We call these devices thermocouples. And a thermocouple is made of, well, let's say you have one piece of material, which you keep one end at the cold location, the other end is where you want to measure the temperature inside a furnace or wherever. And because of the delta T, you get a delta V, or a potential difference across this piece of material. The challenge is that I cannot measure this, right? Because if I put a probe here and a probe here, the internal fields at the contact points will cancel each other. And what I do next is, or what I need to do is that I will use a second material with a different delta, with a different Seebeck coefficient. And in this case, if I keep the hot end together for both of these materials, if I weld them together or make them electrically contact them to each other, this will be at the same potential, but through each one of these materials we'll get a different delta V, depending on their Seebeck coefficients. And therefore, let's say I get a minus 10 microvolt for the top one and minus 5 microvolt from the bottom one. So if I look at the difference between the two ends, the cold ends, I have a 5 microvolt difference that is going to be proportional to the temperature at the hot end. Yeah, that's the number that I mentioned. So it's microvolts that we're talking about. It's usually a small number. You're talking about microvolts per degree Kelvin, kind of a sensitivity. But, and then, yeah, for these thermocouples, you remember that in your equation you had a dependence on current as well as the heat, right? The temperature difference. So you had this current as well as temperature difference. In thermocouples, we measure that voltage with a very good voltmeter so that there is no current drawn. So this part is 0, and the voltage difference is entirely proportional to the temperature difference. But the voltages are nonetheless very small. You're talking about, microvolts or tens of microvolts. So what we do here is that we put a bunch of these fellows in parallel. And you can get a thermopile in this case. And then if you have tens or hundreds of these in parallel and then you produce a large enough delta T over there, you can actually produce a large enough voltage to do some useful work with it, right? So there were radios in the old days that worked with a candle. So they had a thermopile, you put a candle in the radio, turn on the candle, you produced a large enough V that you could drive a very low power interface electronics. Now, one of the things that is going to make us or make our lives easier for MEMS thermocouples is that, well, again, alpha S and I, for the two materials that you use in a thermocouple, alpha S1 and alpha S2, are material properties, but you can have, again, with semiconductors, you can get really large alpha S's. So, they can be a lot more sensitive than metals, for example. And therefore, you can get a very good thermocouple with using micromachining techniques if you can use one of the arms, if you can make one of the arms made of semiconductors. Then, well, temperature sensing is such an important problem that, we are not really going to rely on one type. People have been thinking about this in for many years. There are a whole bunch of different temperature sensing mechanisms, right? So the thermometers that you have seen, the mercury ones or alcohol-based ones, it's based on change in volume. You measure change in volume of that material in response to changes in temperature, and you estimate the temperature that way. Change in resistance, thermistors are used often, not very sensitive and not very accurate, but if you're only monitoring the changes in resistance, in temperature, they are good devices and inexpensive ones to use. The forward bias voltage of a diode is a good metric for temperature sensing. If you bias a diode in its forward bias region, the forward voltage across the diode will drop at about 2 millivolt per degree centigrade. So if the temperature rises by 10 degrees, you will have a 20 millivolt reduction in forward bias voltage. And that's almost independent of how you make the diode. Not entirely, but almost. So it's a very reliable number when you make a sensor. Saturation current of a diode is also a very sensitive parameter for measurement of the temperature, but the issue is that it depends on the diode parameters more than the forward bias voltage does. Resonance is another parameter that people can use. The material properties change with temperature. So for example, if you make a resonator out of silicon, the Young's modulus of silicon is temperature dependent. So when the resonant properties you look at, at the end of the story, the resonant frequency was proportional to the square root of E over rho, if you go back to the dynamics lecture. And if you assume that rho, the density of the material, doesn't change much with temperature, but E does, then your resonant frequency is temperature dependent, and you can use that. You can measure IR radiation as the examples that I showed at the beginning of this lecture, and there is many more. The temperature is such an important parameter that we have a lot of different ways of measuring it, and then which one you pick and use, especially for MEMS and micro devices, depends on what is available in your process. And the second thing is that, how much are you willing to spend on getting a good temperature sensor. In most cases, measuring the relative temperature difference is easy, right? Because, for example, you can have two thermistors, and then, if you don't care about the absolute value of the temperature and you just want to know if this end of the chip is hotter than the other end, as long as you keep the geometry of the sensors, the resistors, they are probably going to behave the same, and you can monitor the temperature differences. Measurement of the absolute value of the temperature is a bit trickier, and in most cases a calibration step is required. So that's that for thermal transduction. We have two more energy transduction mechanisms, main energy transduction mechanisms that we will cover in upcoming videos: electrostatic transduction and piezoelectric transduction. And there is a few other ones that I mentioned as before that are not as common but are very important, and you can use them at large or small scales. So that's that for today, or for this lecture video, and I'll see you later.